Hello everyone, welcome back to the 12th week of our course on measurement and instrumentation, and this is essentially the last week of this course. Today is the first lecture of this week and we will continue our discussion on signal analyzers that we were doing in our 11th week. Okay. We have seen that the signal analyzers were the electronic systems which were used to examine signals in the frequency domain to understand their frequency components, distortion, noise and spectral characteristics. We have seen various examples of signal analyzers including spectrum analyzer, network analyzer, wave analyzers, logic analyzers, vector signal analyzers VSA, audio signal analyzers, real-time signal analyzers, FFT analyzers. We have seen that FFT analyzers can be part of one of these systems also, but separately also you can get FFT analyzers, dynamic signal analyzers, modulation analyzers and so on. Okay. All these signal analyzer instruments or signal analysis instruments measure the basic frequency properties of a signal, but they use different technique for this measurement. And also they highlight different component of the signal. Okay. Like for example, a spectrum analyzer sweeps the signal frequency band and display a plot of amplitude versus frequency. Usually this is operated in a wide frequency range like from 0.02 Hertz to as high as 250 gigahertz. Okay. We have distortion analyzers which usually operate in the frequency range of 5 Hertz to megahertz and measure energy present outside a specific frequency band and indicates the harmonics. Okay. Similar to the distortion analyzer, an audio analyzer can measure additional functions, for example noise in the signal. Okay. Modulation analyzer tune to the required signal and recover the whole amplitude modulated or frequency modulated or even phase modulation envelope for display and further analysis. Okay. Similarly, a wave analyzer measures the amplitude of a single frequency component in the range of 10 Hertz to as high as 40 megahertz. Okay. Usually, any periodic waveform can be expressed as the sum of a DC component and a sinusoidal harmonics. Okay. Analysis of waveform consists of determination of the value of the amplitude, frequency and sometime phase angle of the harmonic component present in this representation. Okay. If you talk about any complex waveform, a complex waveform can be mathematically represented as a combination of a fundamental frequency as well as the different harmonics that I just mentioned. Okay. When I say harmonics, these are the integral multiples of the fundamental frequency that together with the main frequency component form the shape of the complex signal. Let's try to see this with one example. Okay. This V equal to Vm1 sin omega t plus sin 2 omega t and similarly other components are there. Okay. Now this is Vm1 sin omega t is my fundamental component and others are called second harmonics, third harmonics and so on. I am sure that you might have came across these complex waveforms, but I just wanted to repeat it in the context of this course. Okay. Now this shows that a complex waveform is the sum of fundamental frequency and its further harmonics. Okay. Graphical and mathematical methods can be used for the analysis of these signals, but these methods are very laborious and require good amount of time just for single harmonic. Okay. Now the analysis of the complex waveform such that we have just seen can be done by electrical means using a band pass filter network which can single out the various harmonic component and can focus on each of them. Okay. Now network of these type of narrow bands of frequency and now network of this kind of band pass filter can create a narrow band of frequency and provide a high degree of attenuation to all other frequencies and it will not allow them to pass through it. Okay. Now the instrument which utilize such a technique is known as a wave analyzer. Okay. So I can say that a wave analyzer is an instrument which is used to measure the relative amplitudes of single frequency component in a complex waveform. Okay. So you can say that it works like a frequency selective voltmeter which is using a band pass filter. This will allow only a narrow band of frequency to pass and attenuate all other frequencies, so that you can analyze that particular frequency component. Okay. The analyzer is tuned to the desired frequency using a frequency calibrated dial, and this can be a user controlled, okay, to obtain the maximum amplitude, while other signal components can be simply rejected. Okay. The amplitude is indicated either by a suitable method. You can either choose a voltmeter to show the instantaneous value, or you can also use a CRO to see the complete waveform for the previous measurements, as well as you can store them. Okay. A basic wave analyzer is shown over here. You can see that there are different components. This is the primary detector, which is constituting a capacitor and a inductor. Okay, and it has a rectifier component and also has an indicating device, which can be a simple voltmeter. Okay, so a basic wave analyzer consists of a primary detector, which is nothing but this tuned LC circuit, as I have mentioned. A rectifier, this is a kind of bridge rectifier, and the indicating instrument. Okay, the LC circuit is tuned to a particular frequency, so it passes only that frequency component and rejects all other frequency component. Okay. Now, this rectifier once sees this signal, which has a very which is a concentrated signal, I mean kind of very narrow band signal, okay, is the input to this rectifier. Therefore, it perceive it as an AC signal and convert that AC signal into a DC signal. Okay. And the DC voltmeter, which is this indicating instrument, measures the amplitude component of this particular signal. Okay. Therefore, this circuit measures the amplitude of the individual frequency components present in the complex waveform, which was the input to this primary detector. Okay. The wave analyzer must have extremely low input distortion. I mean, it should be as low as possible, and it is sometimes that low that the analyzer itself cannot detect that. Okay. And the bandwidth of the instrument is very narrow, and this is one of the relative response for which is plotted against the normalized frequency of a wave analyzer. You can see that the bandwidth is very, very small. Okay. There are two types of wave analyzer depending on the frequency range. We have seen that there is a huge range of frequency over which this wave analyzer operates, and we have a frequency selective wave analyzer. Usually this instrument or this wave analyzer works for low frequency in this range. When I say low frequency, I am talking about few hertz to few megahertz that we have just seen, for which is the operative range for this wave analyzer, and this heterodyne wave analyzers are useful in the megahertz range. Okay. Let us see this two different type of wave analyzer in little detail. Okay. So, frequency selective wave analyzer is used for measurement in the audio frequency range, which is a low frequency range from 20 hertz to say 20 kilohertz. Okay. Now, this instrument or this analyzer contains a filter section with a very narrow pass band that can be tuned to the frequency of interest. The block diagram of this wave analyzer is shown over here. You can see that you are giving the input to the attenuator, which I am calling the input attenuator. There is a driver attenuator, and there is a series of RC network which is constituting a high quality factor active filter. Okay. And then you have meter range attenuator, output amplifier, then you have this detector and buffer amplifier for the output and auxiliary output for the recording devices, and so on. Okay. Now, if you see this frequency selective wave analyzer, it contains a filter section with a very narrow pass band that can be tuned to the frequency of interest. Okay. The input waveform is applied to the input attenuator, and a driver amplifier feeds the attenuated signal to a high quality factor active filter. Okay. It should be noted here that the input attenuator is set by the meter range switch, which is situated at the front panel, means that it is a user control value. You can tune the attenuator value as per your requirement, and of course, it will depend on what you are feeding to it. Okay. An attenuator is used as at the first stage in a wave analyzer to prevent any kind of overloading. It also helps in maintaining the linear operation of overall circuit and provide proper input signal conditioning for the accurate measurement of the input signal. Okay. The filter that you have just seen, the high Q active filter that I have just mentioned, consists of cascaded arrangement of RC resonant sections and filter amplifiers. Okay. And the passband frequency range is selected by switching the capacitors and tuned using precision potentiometers over the entire audio range, because you are targeting 20 Hz to 20 kilohertz. Okay. Closed tolerance polystyrene capacitors are generally used for selecting the frequency ranges. Okay. Polystyrene capacitors are used because polystyrene has excellent stability. Okay. They have very low temperature coefficient and its dielectric constant changes very little over the temperature. Therefore, capacitance remain almost constant even there is a variation in the ambient conditions. Okay. Further, this particular polymer is a non-polar dielectric material and has a very low dielectric absorption and very low loss tangent. Therefore, energy is not dissipated as heat here, and capacitor behave almost like a ideal capacitor, and that's why it provide you a narrow bandwidth and high Q. Okay. Please note that here we require very narrow frequency band and therefore we need a high Q active filters. Okay, because we know that quality factor, we have already seen this when we discussed filters in detail, that quality factor is equal to the resonant frequency divided by the bandwidth, and bandwidth is nothing but your F2 minus F1, where F2 and F1 are the lower and upper cutoff frequencies. Okay. Now, with high Q narrow bandwidth can be achieved because you can see that this Q is inversely proportional to your bandwidth. Okay. So, with high quality factor you can achieve basically a narrow bandwidth. Okay. Now, you are using not a single RC filter, I mean you are using a cascaded RC filter, because one RC band pass cannot provide you the required quality factor, and usually a single stage will have low Q only. Okay, and therefore a series connection of this RC stage is required. Okay, when you have multiple identical RC stages, your bandwidth decreases and a very narrow frequency band actually passes. Okay, this is exactly what the wave analyzers were needing. Okay, with the RC arrangement, closely spaced frequency can now be separated and harmonics can be isolated accurately, what is required for the wave analyzer. It wished to give you a narrow band output where you can analyze each of the harmonics. Okay. However, when you have this kind of cascaded RC arrangement, it causes other problems, like each RC stage reduces the signal amplitude, and after multiple stages signal becomes very weak. So, what could be the solution? For weak signals, we have already seen that amplification can be one of the solutions. Therefore, you have seen that filter amplifiers has been inserted between or after the initial stages. Okay. These amplifiers restore the signal strength. They also helps in maintaining the signal clarity and prevent loading between the subsequent stages. Okay. The selected signal or selected frequency is then passed through a final amplifier and a buffer amplifier to the meter circuit or external devices like any recorder or electronic counter. The instrument has very narrow bandwidth that we have seen, typically about 1% of the selected frequency. Okay. So, this is how frequency selective wave analyzer actually work and achieve this level of narrow bandwidth. Okay. Now, this is the story of low frequency, like here you can operate from 20 Hz to 20 kilohertz, but I have mentioned that wave analyzer can be used for even for 20-30 megahertz signals also. Okay. For those kind of signals we use a heterodyne wave analyzers. Okay. So, they can be used over a megahertz range. Okay. The input signal here also passes through an attenuator and amplifier and is then mixed with the local oscillator, and this is a typical block diagram for a heterodyne wave analyzer. You have input signal, it is fed into a attenuator, you have input amplifier which is amplitude controlled. Okay. Then you have oscillator and a mixer which is generating a frequency f2 and you are feeding this signal f1 from here, and this mixer 1 is giving you a signal say f2 minus f1, and this is fed into a intermediate frequency amplifier. Okay, then it is again fed to a mixer 2 which is connected to a fixed oscillator, and this is given to a active filter, and then it is fed to an amplifier before it is displayed or shown on a meter. Okay. Now, the local oscillator frequency is adjusted to produce a fixed frequency output within the passband of the intermediate frequency amplifier, which is the next stage. Okay. An intermediate frequency amplifier is a fixed frequency high gain amplifier and also used for other heterodyne applications like super heterodyne receivers in radio, TV, radars, etc. to boost the signal after it has been down converted from a high frequency. Okay. Now, the signal is then mixed with a second crystal controlled oscillator so that the output from the mixer is centered at a 0 frequency. Okay. Because you have seen that my output was f2 minus f1, it is adjusted in such a way that the output is exactly at 0 frequency. Okay. The active filter with controllable bandwidth selects the required frequency component and send it to the indicating meter. Okay. In a heterodyne wave analyzer, the local oscillator frequency may slightly change due to temperature drift or circuit variations. Okay. And therefore, we use automatic frequency controls. Okay. So, using automatic frequency controls, the oscillator automatically adjusts and locks to the signal frequency, so the frequency remains stable. Okay. Good frequency stability in a wave analyzer can also be obtained by using frequency synthesizers which have high accuracy and high resolutions. Okay. Frequency synthesizer, if you do not know, is an electronic system which is used to generate a wide range of precise and stable frequencies from a say single reference oscillator. Okay. There are usually two methods or two ways by which you can use this frequency synthesizers, or you can say that there are two different types of frequency synthesizers. One is direct and another is indirect. When I say direct, I mean you are directly using the oscillator. Okay. So, direct frequency synthesizers uses a stable crystal oscillator followed by a series of harmonic multiplier and mixer to provide the range of different output frequencies. Okay. Indirect frequency synthesizer uses a phase lock loop to give an output which is a fraction of that of a stable crystal oscillators. Okay. This synthesizer can provide excellent frequency accuracy and stability, but careful design is needed to overcome the problem of noise in the output. One such design of a frequency synthesizer by this indirect meaning, okay, or indirect frequency synthesizer is shown over here. You can see that I am having reference frequency f1 which is fed to a phase detector. Okay. The output of phase detector is fed into a low pass filter and then it is amplified using this amplifier. Okay. Then this signal is fed to a voltage controlled oscillator where I am also applying set frequency and a programmable divider which is a user control. You can say that here I have put a select setting, means that it is a user controlled parameter, or you can say that this factor n is at least the user defined parameter. Okay. Defined parameter, right. And then this programmable divider where I am dividing this with a value n to give a output f2, and again it is fed to a phase detector. Okay. Now, the output of the phase detector is a signal which is proportional to f1 plus minus f2. Okay. The low pass filter selects the signal which is then amplified as you have seen over there. Okay. And the output of this amplifier is fed to a voltage controlled oscillators. Okay. The output from this VCO is fed to a programmable divider and then back to the phase detector. The system drives f2 towards f1 until they are equal. When I say they are equal, I am talking about their frequencies. Okay. And at this stage there is still a phase difference between the two frequencies, although they are matching in their frequency, but still there is a phase difference between them. Okay. Now, when you have this kind of phase difference and these frequencies are equal, okay, it will produce sufficient DC signal to keep F2 logged to the initial frequency F1. Okay. Now, the output frequency here is NF, and this can be changed by varying N, or you have seen that it is controlled by the programmable divider. Okay. The switching speed between frequency settings of this frequency generator depends on the time needed for F2 to lock to F1, and it will also depend on one more parameter that is known as setting parameter or setting time. Okay, we'll see what is setting time. Okay, for large frequency difference, the lock time can be long, okay, and it can be minimized by setting the VCO very close to its final value, usually under controlled by say some microprocessor or microcontroller, and then letting the phase locked loop pull it to some exact value. Okay. The setting time basically is the time after the lock for the output to reach within a given range of the final output setting, and it is typically in the range of few milliseconds. Okay. And this is how a frequency synthesizer can help the wave analyzer or heterodyne wave analyzers. Okay. Now, the applications of these wave analyzers are tremendous, as I have mentioned earlier, and three important applications of wave analyzers are in the electrical measurements, in sound measurements, and in the vibration measurements. Okay. Let us see one example that how these wave analyzers are very helpful for industry applications. Okay. They are used in industry to record sound and vibrations produced by rotating electrical machines and other heavy equipments. Okay. Also, they are used to identify the source of noise and vibration before it can be reduced or it can be eliminated. Okay. A fine spectrum analysis with a wave analyzer shows various discrete frequencies and resonances that can be related to the motion of machines or different parts of the machines. Okay. Once these sources of sound and vibrations are detected with the help of wave analyzers, there can be different measures that you can take to eliminate these errors. Okay. Similarly, you can think of its application in other industrial processes as well as in the laboratory conditions also. Okay. Therefore, I think wave analyzers are very crucial, particularly in the frequency range that I have mentioned over here. Okay. In the next class also, we will continue our discussion on signal analyzers, and we will see some more analyzers which are useful in these industrial settings. Thank you.